Let's get start now. So we started from very basic, starting how we can acquire. Although this is not exact our domain, you should have knowledge that how the image is captured. What is the difference between different images? And we talk about it, that the difference lies in the range of the figures. And we have very good figure as well here. This shows like various spectral images covering the large part of the spectrum. Whatever is the image, the basic processing techniques will be same. First part, why the sampling and quantization is needed. Yeah, one of the main thing is the storage, because if we don't sample, we have infinity levels and infinity size, okay, and cannot store it, right? So we need a sample, take the samples of that, and the sample itself has a value that can vary from 0 to infinity. Put the value, still we need to quantize it. So first we take the sample, then we quantize it in limit numbers in order to make it feasible to store the limit. Fine. So we discussed in details some of the part, and this is like the sampling. So in 1D and sampling 2D will be just taking the samples at equal distance of the 2D layer. This layer. So this sampling, and then definitely once we sample it, we quantize it, and we should have a levels, and the sample that is in between the level we can round it off. Let's say we want to store this image into the computer. So definitely it will be in terms of bits. There is a direct relationship between the quantization level and the number of bits that we store. Because we have to store these levels inside the computer, inside the memory. In terms of bits are 1, 0, right? So what are this relationship? The number of levels is equal to 2b. B are the number of bits. Let's say your memory is 2 bits, just 2 bits. So how many levels I can have? 4. Similarly, 4 then becomes 16. But for images, we have b equals to 8. It is standard size 8. So what will be the levels? 256, ranging from 0 to 255. Here, 1 pixel. You can have a value from 0 to 255. Normally, the image size is again the power of 2. Let's say 256 by 256, or let's say 4 by 64. How many bits will have? 1 bit, 1 pixel is how many bits? 8. So if an image is 64 by 64, then how many bits will have? 8. See, and this is the problem. This is the problem. The image, that's why it takes a lot of numbers.
I mean, that's why when the pixel increase, the size of the same thing bigger, so it's become even bigger and bigger.
Because we said that the level we can go maximum was 255, so this is the quantization level, right?
Yes.
Yeah, and here we said 2 to the power of 8, that is 256.
Yes.
So what is 255 and 256?
256 are the number of levels, but from where to where? From 0 to 255. Here, you see how many levels you can see here? How many levels? A short 10? 11. It's 11, right? The number of levels are 11, but it's starting from 0 to 10. So similarly, if you have 256, it will start from 0, so it will go up to 255. Okay? So fine. Yeah, I have a lot of examples, so we'll see about this. Yes.
It is 8, it's a standard or what? Some people mention the root and the
You can go by 256 in the it's yes, it's okay, but you can go to 512, you can go lower it to 64. Yeah.
This is 64 by 64 and 8 bits.
It is. So how much bits are required?
Why you selected 64?
Just an example.
Okay, 64 and
64 yes, samples, and each sample is 8 bits. We will come to that. Yeah. So you see, this is the real image file. This is the which image? Digital, yeah, digitalized, which is sampled and quantized, and this is what it is in terms of numbers. This is again what we said. We said that 8-bit quantization, we have 256 gray levels. Huh? The levels are gray. Each level indicates a color. 0 means black and 255 is white. That's for sure. Then we can also have 1-bit quantization, but that is only valid for black and white. What is different between the gray level image and the black and white image? Yeah, it can be this, but so black and white has just black and white. Nothing in between. Yeah, 1 0.
So each number has 1 0.
Yeah, 1 and 0. That's then the sampling. Maybe you have your screen and you can see these numbers on your monitor, right? Have you seen these numbers?
Yeah.
What are these numbers? These are the actually pixels of your screen. These are the common sizes. Digital video, again, we have a pixel side, but we also have the frame rate. Basically, what is video? Video is just moving images. Okay. Sampling has a direct relationship with the pixel. So number of pixels equals to number of samples. And total pixels equal to total rows and total columns. Fine. So now this is all the things we have studied, but just to summarize it, we have image f, x, and y. What is f, x, and y? X and y is the pixel, any pixel inside the image. Fine. And then x is now, where is x? In this direction or this direction? In this direction, this is just a notation that is being used in some of the books. Some of the books also use other notations, like they take x like this and y like this. And why it has been taken like this? Because you see, actually, this image is a kind of I can plot it in a 3D because it has the amplitude, right? So I can plot, if I plot in amplitude, it will look like this. So if I'm looking from this side, if I am looking from this side, fine. So the x will be like here. X will be like here and y will be. So it's like some sort of imagination that I'm looking at the image with the amplitudes, and this is x and this is y. But this is, and also this is the, I will say, the convention that is used in the book. Make sure normally we take this as y and this is x, but this is the opposite in image. But not always the case. We can use that. What else? So x has some pixel ranging from 0 to m minus 1. Y has a pixel ranging from n minus 1. So the actual size will be m multiplied by n, and if we convert it to bits, multiplied by the number of bits will be total bits, just k. Or again, this is what I said. You can have y here, x here. You can have this notation. You can have this notation. So what makes the difference is that this is the origin here. So the first pixel will be 0, 0 here. But here, the origin is here, so we will make this pixel as 0, 0. And here, and this is the convention that I will be using. I think this I made it wrong. In the textbook, sorry, I just put it here. Should be here. So now we convert an image, the real image, the name, into pixels or the samples. So in a matrix form, I can represent it like this. In the paper, if I want to do it, this is my image.
Each one is a pixel.
It's a pixel, and its values goes from 0 to 255. Similarly, this is again, sorry, this is x, this is y. Again, I think I just put it wrong. I will just correct it. And this is also another notation. Another notation of the same thing. Either you can represent it like this. More in the book, they represented it in f of xy. So again, go more deep. This is the image that we look at in our daily life. If we zoom in, you can say that this is the pixel. It has a value. Now, what about color? What about color? Yes, y3. Yeah. So we know we already have some idea that we have 3 primary colors from which other colors are formed, right? So what are these? Red, green. So from red and green, blue, we can find other colors. Yes or no? Yeah. So for the color, each pixel will have 3 values, not one. One for red, one for green, and one for blue. Okay. And based on that proportion, when we combine them, we find something. Let's say one is both are 0, one is let's say 1 or 255. So you will see that combination.
So here we have 3 values.
Yeah, fx and xy will be 3 our term.
3 bits.
No, one will be one will be again 8 bits. So now you have everything same but multiplied by 3. So in other words, so for example, you have image 1, 2, and then 3. Yes, to get color image. Fine. This is left.
Not here now. We have three colors, right?
Yeah.
But how it can be combined? The colors is not linear blue, but the original is linear blue, right?
So this is the good thing. If you have these 3 colors, you can have any color.
But how do you represent the other one? Now we have 3 colors, then it become what's you saying?
The conversion method. So this is what I think. Just wait for the whole chapter.
Yeah, this is now my question. We have 3 and how to represent the other colors.
Yeah, 3. But yeah, so but 3 is the proportion. These 3. This is a bit greenish. This is orange, and this is yellow. So you see the proportion. Proportions are different.
The proportion of the 3 colors.
Yes. So the proportion of 3 colors will define other color.
So the defining of the proportion is define the exact color what's used in that.
Yes. Fine. So fine. So this is what we have. We have a pixel coordinate, which is a xy, which has a value, and so when we say pixel, it either represents one of them or both of them. But normally when we say pixel, pixel has a location plus the amplitude, the value is actually the pixel, both of them together. Again, this is just an example. If you zoom in, so it's a number, and if you know the numbers, then you can manipulate it. So just want to go deep here. Maybe I can give you an example for quantization and sampling. Let's say you have the image. So can you do for me quantization and sampling? That will just result in 2x2 image and 16 quantization level, like L is equal to 16. Can you do for me this? 2x2 sample and 16 quantization levels for this. Let's assume this is a continuous image. Can you do any 2x2 image? Yes.
Here we can say, for example, if we will take a normalization between 0 and 2 to 16, for example, the maximum here will say
Maximum is what?
what is the maximum in this image?
This is 15. No, not both the next. Just discrete. I want to discrete.
0 and 2.
First take the sample. Yes. First take the sample.
Yeah.
Take the sample, then quantize it. 0 to 15. Yes.
Last one.
So 15. It's 15.0, 3.2. You can take any numbers close to that.
It is now 2 by 2, right?
There's more than 4, but again, don't consider it to be 4. I'm just giving an example of continuous image. I cannot draw a continuous image. So just assume it to be continuous and take the samples equal distance so that on the x-axis we have 2, y-axis we have 2.
Yeah.
Fine.
Phone number as a square.
Did I ask you something difficult? What can I do? But how to sample it? To get 2 samples equal distance. So what I will do? I will pick. So I will pick 2 equal distance here, right? And the 2 equal distance here. Fine. So it means that I took this one and this one equal distance, right? So now my image will be 2 by 2, right? What is 2 by 2? 7.1, 3.5, 3.2, and 15.0, right? Now quantize it from 0 to 15. So whatever is there, we have to round it to the nearest, because we have in the original image goes from 0 to 15. Already is there. So what it will be after quantization? What it will be? 7. 3, not 3, it will be 4. You have to see that how much is the maximum, how is the minimum, and also the levels. Now here it goes from 0 to 15, or the maximum is 15, so we just need 16 levels. However, so what I want you to do is that if instead of 16, if I use 4, then what will happen? And somehow you will say you already there.
Yeah, the same. For example, 7.
Yeah, that's what I want you.
By 4 or 15.
I want you guys to please change this example, not now. Maybe this is your task, okay? To change this example so that L should be equal to 4. But if you do this, you will understand everything clear. You see what I'm saying? Instead of 16 levels, now I have 4 levels because my capacity is 2 bits now.
Yeah, because now when we started putting the numbers at the beginning, we were considering the 16 level. So even maximum we went to 15.
Yes. No, this wasn't the case. This I took it. This is what I'm saying.
Okay,
But I wanted to give you an easy example and then ask you to think if I have the less levels, then what will happen? How to do that? 4 means that your levels can go from 0 to 3. We discussed it that for black and white we have 1 sample, for gray we have 1 sample, but how many bits? 8 bits. Here 1 bit, and here we have then 3 samples per pixel. Is this clear? This is again example. This is an image, and if I have these 3 colors that I need to store, and from these 3 colors I can have color image. Fine. This again is a similar thing. This is again an example. So I put a lot of examples. So this image in terms of black and white, you will see all zeros and ones if you have black and white image, right? Because each pixel will be either black or white. Fine.
This is an example of black and white.
Black and white, yes. So like in the matrix form, you'll just see 0 and 1. Fine. So in the gray, you will see some numbers ranging from 0 to the maximum quantization level -1, whatever the level is. It could be 255, or it could be other, where the 0 means black and 255 means the bright or the white. This is vector value. You can also call the color image as a vector value because you have 3 values per pixel. Fine. And this again example. So we already talked about it. The number of bits that are required for an image is the dimension, n is the other dimension. So m multiplied by the number of bits. And this is just a table just to show you. Let's assume that n equals 32 and image is a square image where n equals to m. Both are same. So if let's say you have 32 by 32 image and you have 1 bit, k is equal to 1, means 2 levels. 1 bit means 2 levels, right? So if you have this, how many bits are required to store the image? 32 multiplied by 1, which is 32 by 32. And similarly, the same image, if you have 2 bits, 32 multiplied by 32 into 2. And similarly, you can see that if you have 256, and how many bits we have? Let's say we have 8 bits. So how many bits are required? Total number of bits.
What is the meaning of 32 and the equal to?
32 is the size of the image, 32 by 32. X and Y. Yes. And K is the number of bits. The number of bits per pixel. So if you have 32 by 32 and 1 becomes 32 multiplied by 32, which is 102. 4.
It's the level 22 by 2 because
Yes.
here 1000 it will be 4.
Total number of bits.
2 by 4.
No, 1 bit. 1 bit per second. Yes.
1 bit is 0 and 1.
Yes.
32 is n.
Yes. And
Oh, and then what did we say n times n?
because n is 1 dimension, and I said let's assume you have 32 pixels here and 32 pixels here. So total number of pixels will be how many?
1020.
Yes, and 1 pixel, 1 bits per pixel, 1 bit per pixel, right? We have. So it will be 1024, right? Let's say you have a decimal number 4 or 3. How to convert it to binary 0 1? How to convert a decimal number to a binary number? We can take, let's say we have 0 0 1 1. So how to map it? This is 0, 1, this is 2, and this is 3, right? So what's the relationship? How it becomes 3? We have
0 0 0 0 1 1.
we have this, right? This relationship. Yes or no? Yes. And this is called? This is called least significant. Why is called least significant? This is right is 0.
In terms of
But it's 1. 2 power 0 is 1.
like exponentially, it's the least one.
Yeah, this is the answer, right? So the weight of this is the minimum as we go towards the right. It is. So we can represent a decimal like this. So here, if I have an image and I want the bits, so I can start because it's like going from 0 to 15. If you can see 15, so it means that number of levels will be 16. So if you have a 16 levels, so I can represent 16 levels into 4 bits. So 2 to the power 0 multiplied by this plane. Yes or no? Yani 8 is what? 0 0 0 1 is 8. So this we call it bit plane.
The number of these matrices was dictated by the highest number here.
In this case, yes.
Because here the maximum is 15, so I can make it with.
Yes. 4. Because 4 means that you have 16 levels, right? Now, see, we always call LSB, MSB. So I will show you the trick here. If I just take an image and plot only this, so I get this in terms of 8 bit. This is 8 bits plane, real image. So you see the more information. This is MSB. Then some less. It means that call it least significant as the less information. See that? It's just nice, right? Yes or no? And this is one of the methods for compression as well, that we just discard some of the low bit planes and just start with this. In this way, I can store less number of bits, so it's a compression. Okay, although I will lose some information for sure. So that's why we call it least significant and most significant in terms of image. This is a real example of the image, and this is just a number, so they are not mapping each other. It's not duplicating. It's different. Let me tell you my way of presenting it. All my presentations or the course will be, first I will present the method, then I will give you a numerical example. Numerical example means like the matrices, and then I will show you the real image, and then at last I will show you the code of that. Fine. So does it mean that these two are related? Now here I just took an example which is not of this example. This is a real image. Like I have to do some coding to upload this and convert this to these bit plans. But how it's been done? It's been done like this, because these are also numbers, right? Numbers, I just multiply with 2 power 3 and the corresponding matrix to get this thing. And each of them, you can see that they are actually 0 and 1. 0 and 1, which makes sense because here is 0 and 1.
So the example on the right, it doesn't.
It's not, yeah, it's just an example, and this is a real example. This is a numerical example. So this matrix does not come from here. It's just a different example.
It's plane 7, plane 6, 5, 4.
This is a bit plane 0. This is a bit plane 1. Okay, so I think we already discussed. Let's say we have less number of samples. So what will happen? Less number of samples. What will happen? And less number of permutations. What will be the effect on the image? Less number of samples means that we are missing details, right? Yeah. And less number of levels means we are missing the sharpness. Yes, can be sharpness or the light information. The intensity will be less. Fine. So now it depends. Sometimes if the image has this image has a lot of small details, minor details. So if I just do less sampling and if this is the original image, then I just reduce it, the sample numbers, then again reduce it, and you can see that I start missing some details. You can see that? Yeah. Because of the less number of samples. But if the image is very like smooth image without less detail, like very close to the face, if you are taking your picture very close to the face, so it will be less details. Because less details, you can have less number of samples. So it depends on the application that what number of samples or the quantization levels are needed. So anyhow, this is again the same thing. If you have a less number of samples, the shape of that image will affect. Similarly, if you have a less number of quantization, you can see more details, light information, more detailed light. But here, it's, you see all these are four same. In actual image, there's some shade. But since I quantized it, I lose that information, right? So anyhow, this is what we said already. Now again, as I said, this depends on the image itself. Like here, you have more details, so more samples. But the quantization level is you can compromise here. But here, you see the shades. So the samples you can compromise, but the shade you cannot, because otherwise the beauty will not be there. Fine. So this is what it depends on the
What's the difference between the two? Now
because here you have more details.
Yes.
More details. So if I lose one sample, I will lose because there are a lot of faces. So I will not be able to differentiate.
the sound.
Yes.
But
here,
it can be, yeah.
yeah, it can be same because you see here almost same color. So samples you can reduce the number of samples. But the light information, if you see, if it's gone, it will the value of the picture will not be there.
What do you mean the light information?
The lighter and darker parts. Okay, of that. I will show you now this effect of sampling, less sampling. So let's say if image is 1024 by 1024, I reduce the sample, reduce and reduce and reduce. So you can see still you haven't noticed anything, right? The size is reduced, but in order to compare, you should have equal size of all of them. In order to do that, if I just make all the size equal, you can see more samples and less samples you have effect. So what is the effect? The shape, the textures are not visible. Now the quantization. Let's say you have a less quantization, what will the effect? It's a very good example. This is like 8-bit. You can see the shades, but as I move to 7 bits, this is like using the 7 levels, 6 levels, and as I go like this, you can see that I am not having that detail that I had there. So now you may have in your mind that what quantization can do and what samples can do, and how important they are. Let's yeah, number of samples you decide using the Nyquist theorem. What is it? What is the Nyquist theorem?
In order to obtain
The number of samples. Minimum. Yes.
how much
Maximum depends on your storage. So maximum in the storage, minimum is so it will be decided by the Nyquist theorem. The maximum frequency in your signal for the image. So for samples, frequency is greater than equal to that maximum frequency in your signal for the image. Yes. But this we will cover in the Fourier transform. That's why I did not discuss it here. And this is again the same thing. If you reduce the number of levels, more details, but as you start reducing the levels, you can see that it's reducing the how much is enough, how much samples, how much this. So first thing, definitely there's a minimum maximum for the samples, and similarly minimum maximum for the quantization. However, it depends on the application. Let's say here my focus is the number plate. If my focus is the number plate, I need more information because it's very small. But if my information, my intention is just to know the car itself, then I think this information is still
So like in the phone when we click on the camera to
zoom in or out.
But that's like
not to zoom in, to make sure that the small number in the figure is catch up.
Yes. One other thing that we will be using it, that we call it neighbors of a pixel. So it's nothing but if you have a pixel and all other pixels that are nearby are not the neighbors. For example, if this is a pixel, that is I am doing some operation here. So this is my concentration. We'll discuss some methods later on. So these are its neighbors. So we call it the diagonal neighbors. These are diagonal neighbors. This is the vertical neighbors, and this is the horizontal neighbors. And you can see that how I just did it. This is x and y. So this will be x minus 1, y. Yes. Because this is x-axis and this is y-axis, and this will be y minus 1 because I'm just going in this direction. Similarly, this is x, y plus 1. So I'm just mapping based on that.
So making a reference.
Yeah, making a reference.
So it should be like x, y minus 1 could be my reference, and I start
You can do that, yes. However, because of some operation, I will talk about it. You have to consider an image with the neighbor. So I think this little representation is helpful, more helpful. Now, the thing is, let's say we give an example and we said we reduce our image, let's say, but I want to recover it back. Or I want to resize it. Let's say you send your images to WhatsApp and open mobile. It's like it's good, you're looking good, fine. But now you want to display this to your big screen. So how to go back?
interpolation.
Interpolation. Linear by you can see this. So one of these things are either we use the contribution from the 4 neighbors or 16 neighbors or using some advanced methods, but we will not look into this. We just take ourselves to 4 neighbors or 2 neighbors or something like that. So one of the method is the nearest neighbors, which is just replication of the pixels. Just replicate the previous one. Okay, so what it will be, let's say you have 1, 2, 3, 4, 5. I want to increase by 1, so I will just replicate the previous one, put 1 inside. Similarly, if another step, again I replicate.
How we can know that, like when the pixels were lost, what if the levels were also lost in them?
Yeah, definitely we are not recovering exactly the same. We are just interpolating it, we are just estimating.
I mean that for the 4 levels, these are constant, or like we have 4 levels, 3 levels.
I'll discuss 4 levels of this. This is different. So is this? So what you will do? Let's say you have an image and you want this 4 by 4 pixel to be 8 by 8 pixel. So what you will do? You will put 1 row and 1 column after each of them, and then replicate them here like this. Fill it up. This is yellow. This is blue, brown. Just like replication. So I will give you an example. Example of this is here. Let's say I want to have 3 by 3 becomes 6 by 6, double, right? So how to do that? First I have to put columns. So I have 10, 2, and 9, right? So I will put a column here, then say 4, 18, 14, and then 22, 7, and 25. So what I will do, I replicate this one. Becomes 10, right? Previous. This becomes 2. This becomes 9, 4, 18, 14, and even if I want to do another one, it will be that. Now after that, I have to put rows. So if I put rows, I have 10, 10, 4, 4, 22, 22, then again the same row. Yes, repeat the same. Then again, second one and third one. So I will get this thing. Bunch is just like a repetition. This is simplest method. Now let's move to more advanced one, which is called bilinear interpolation. Interpolation. For that, we have a bilinear equation that we need to fix. In order to find a pixel, I have to use this equation. How to use it? Let's say this, and here the neighbors of the pixel come up. So we have to use the 4 nearest neighbors. For 4 nearest neighbors, you have to use these red ones to find out these unknowns. So let's say you have 2 by 2 image, and I put 1 row, 1 column, and 1 row here. Okay, so in order to find all these, I have to use these 4.
So the blue is the missing.
The blue and black one is the missing. Yes, these are the missing. So I had 2 by 2 image, and I put 1 row and 1 column, become this image, and now I have to find this.
Again, we have the red one, and we need to find the blue one, right?
We have the red ones, and the other ones are not there.
Even the black one?
So one way is, yes, one way is, although my origin is here, right? Origin here, but sometimes it's useful if I consider this as the origin in this example. It's up to you. You can consider any number. You can consider, let's say, x equal to 5 and y equals to 5, let's say, and try to find out these values. It's up to you, but it will have more computation. So for simplicity, I assume x equal to 0 here and y equal to 0. For simplicity, yeah? You can use any number. Fine. So now, so if I assume x and y equals to 0, this table will reduce to this table, right? Now I will use the equation in order to find it. So assuming I have this matrix or the image, and I want to find out, I want to rescale it or resample it to higher order, right? So how to do that? I put 1 row and 1 column. Now what are these? Are unknowns, and we need to find it using this table. And not only this table, but let me do it here better. So what was the equation? Can you recall the equation? Plus cxy plus d. So which one do you want to find? Let's see find this one. Huh? So this one is 0, 1. So v will be equal to v of 0, 1, and that will be equal to, because this becomes 0 because x is 0, this becomes b. So we have b plus this again 0. So what I need is d and d. Now as the name suggests, we have to go to the nearest neighbors. Nearest neighbor of this is these 2. These others I don't know, right? So I only know these 2. Let's find it out. 2 is minus 1, 1, right? So v of minus 1, 1 will be equal to minus a plus b plus minus c and plus d. And this is equal to, fine. And what about this one? b 1, 1 is equal to
A plus B plus
a plus b plus c plus d equals to 4. So if I add these 2 equations, now I have 2 equations, and I need b and d to be found out. Yes? If I add these 2, what I will get? Plus 2. These 2 will be cancelled. These 2 will cancel. We can b plus d equals to 2b plus 2d equals to 6. And if you want to find b plus d, so b plus d will be equal to 6 divided by 2, which is 3. So it means that this is 3. I will show you another simple method as well. This one? This is example. Oh, it's just example. Similarly, if you want to find this one, what you need to find? 0, 0. So this is, if I put 0, 0 in this equation, I have to find d only. For d only, what are the neighbors? 1, 2, 3, 4 neighbors. So I have to put each of them to find d, the same way I did it here. Yes, you can do it by yourself. Let me know if you have any problem. Then let me show you a very simple way of the same thing. Let's say you have this image 4 by 4. I want to apply this method, which is called bilinear. So what I will do, first I have to insert column, and for each column I will take the average of side by side. Average of side by side.
So you want to convert from 4 by 4 to
to 7 by 7. So this is only for bilinear. Bilinear. One method I told you already, using equation. This is another simple method. First put column. These are the columns that I have already inserted. This column and this column. And I just took average of these two. I put it here. Done. Now put the row and take the average of above and
below.
this will give you the same answer as we did by the equation.
The same answer?
Yes, it's for bilinear. This is for bilinear. No? Get my point? No. Either use that equation or choose this. This is easier. Just take an average. That's why it's called bilinear, because we are doing linear first and then linear addition being purchased.
It was like 4 by 4 converted 8 by 8. Like here it was perfect. I can't take
Yeah, yes. So for that you can. It's up to you. You have to define the rule. You can insert another row and column in between and use the same rule. Now so it's what 7 by 7, right? So if you want to have another one, put it in the middle. Let's say here and take the average. You can see this is actually average of these two. This is average of these, and this is average of these 4.